The problem statement from GATE Physics 2017 reads as follows. For the transistor amplifier circuit shown below with R1 equal to 10 kilo ohms, R2 equal to 10 kilo ohms and R3 equal to 10 kilo ohms and beta equal to 99. Neglecting the emitter diode resistance, the input impedance of the amplifier looking into the base for the AC small signal is dash kilo ohms. This is a numerical answer type question and we need to find our answer and then round it off to 2 decimal places and we'll fill in the blank here.
And the video is clear, audio as well as the visual. Is it clear? Please respond.
Yes, sir.
Okay, I'll continue now.
So just getting right to the problem. So this is the BJT that's given to us. It's an NPN BJT and it says that it's an amplifier circuit, and for this we have to perform the AC analysis. So how do we go about doing it is that we first need to understand what is the model of a BJT as far as small signal analysis is concerned. So this is the BJT that we have, NPN BJT with collector, base and emitter. The current will flow out of the emitter. DC analysis. So this is the conversion, this is the model that we use for the small signal analysis. So you can see that the base terminal is over here on the left, the collector is on the right, which is on the top over here, and emitter is at the bottom as always. Now in the question it was given that we can neglect the emitter diode resistance. This means that we can effectively ignore this resistance R pi here. So by ignoring we assume that this to be 0. So effectively our BJT for small signal analysis can be converted to this. We have assumed R pi equal to 0. So this is the circuit that we finally get. Now what I'll do is that I'll plug in wherever BJT is used. I'll plug in these circuit elements. So everything is a wire except for this dependent current source, because this is a current source as indicated by this arrow. It's dependent. This is dependent on the IB, where beta is the current gain of this transistor, DC current gain of this transistor. Now this was the circuit given to us. So what I'll do, I'll simply replace this BJT with, I'll plug the BJT model that we have developed over here. So I've just done that. So in removing this, so it's R1, R2, VCC, V in all remain the same. R3 also remains the same, and the V out, the port remains the same. Just that base, collector and emitter have been replaced with this. So so now moving forward, this is the after we got this result after the first step. Now the second step is to remove all the independent DC sources. Now remember, I'll point out independent DC sources. So what are the independent DC sources that we have here? So first independent DC source that we have here is this VCC. It's an independent DC source, DC voltage source. So we'll put VCC to ground. By removing, we mean all the independent voltage sources should be grounded, and all independent current sources to be open circuit. So all dependent current source to be open circuit. Now note that this is not an independent current source. This is a dependent current source. See this term here. So this will not be open circuited, right? But VCC, similarly, V in is a dependent, is an independent voltage source, DC voltage source. So this will also, we can also ground this, right? So what we'll get something like this. So see, VCC is grounded, right? So if you ground VCC like
Excuse me for a minute. Someone is trying to join. I'll replay the video from here.
So if you ground VCC like this, so what so see, VCC is grounded, right? So if you ground VCC like this, so what I've done here is that, so R2 remains the same here, this circuit remains the same. So R1 is between the base, which is this node here, and the ground, VCC's ground. So I've just rather than this leg should be up, I just put it down. Nothing has changed. So everything remains the same. Similarly, this collector will now be grounded because VCC has been grounded. So this remains the same. So this is the circuit that we have gotten. So I'll reiterate that remove independent DC sources means all independent voltage sources to be grounded, just like VCC, and all independent current sources to be open circuited. There are no independent current sources. This is a dependent current source. So nothing will change over here. And this is the circuit that we had. Now in the third step, we'll put a test source. So where we had to find the input impedance. So what we'll do at the base, this is the base, we'll put a test source. So this is the V test, this is the I test. So we have put a test voltage source, and we'll measure the test current, and we can simply define the input impedance is nothing but V test over I test. So whatever current we are pushing in the denominator, and in the numerator we have the voltage, the AC voltage, small signal AC voltage that we are applying. And the denominator.
So what the analysis over here is, this is a very common feature for AC analysis. So wherever you want to find the impedance, you put a test source over there and you feed in and you try to measure the current, and you divide the two and you get the input impedance. So for instance, if we were required output impedance, we would have put a test source over here at the collector, and we have measured the test source. But since we are talking about the input impedance from base, question explicitly asked, hence we are putting a test source at the base, and we'll simply measure the test current, and we'll obtain the input impedance using this very simple formula.
And in the numerator we have the voltage, the AC voltage, small signal AC voltage that we are applying. Now, so this is the final the circuit diagram that we have over here, and these are the constants that were given to us in the problem itself. What we need to find is the input impedance, which is defined at V test over I test. So we'll start with that, and let's just first define a couple of currents which I've defined here. I1 is the current flowing through the resistor R1, I2 is the current flowing through the resistor that we have here R2. Now what I'll do is that so we'll look carefully and look at this node, the emitter node over here. So this voltage is nothing but V test, right? This is nothing but V test, and this is just a wire. So all the voltages here will be V test. Similarly, this will also be, let's call this for the time being VE. Now first what I'll do is KCL. I'll apply KCL at voltage at node VE. So incoming current is nothing but this IB and IC, right? So I'll write it as IB plus IC is equal to IE. So I'll get IE equal to simply beta plus 1. This is what I'll get, and what I'll do if I apply Ohm's law across this resistor, right? So I'll write this as well. So I'll write Ohm's law across R3. So I'll write that will be VE minus 0 is equal to IE times R3. And now I know the value of IE, and VE will be nothing but V test. Note that this is just a wire. This over here is just a wire. So VE will be nothing but V test. So I can write V test is equal to IE. The value of IE is nothing but beta plus 1 times IB times 3, right? So this is an expression that we have obtained, and from this I can write IB is equal to V test over beta plus 1 times R3, and let's call this expression 1. Now in step 3, what I'll do is I'll apply KCL at this node. Let's call this as Vin node. KCL at Vin. So we'll put all the incoming current. So incoming current is nothing but I test. So you see this is the incoming current in the blue that we see here. The outgoing current is nothing but I1 plus I2 plus IB. So I'll write I1 plus I2 plus IB. So I'll get I test equal to, now I1 is nothing but, so we know that this voltage is nothing but V test. This is a wire. So this will come out to be V test over R1 plus V test over R2. And we know the value of IB from expression 1, which we'll use here. So that will be V test over beta plus 1 times R3. And from this, I can get I test is equal to V test. This will be R1 parallel R2 parallel beta plus 1 times R3. And thus I'll get V test over I test. V test over I test will be nothing but, so sorry, this was V test over this. So V test over I test I'll get is R1 parallel R2 parallel beta plus 1 R3. So this is 10K parallel 10K parallel. So beta is 99, so that will be 100 into R3, that will be 100K. So that will be, if we this 10K parallel 10K is 5K, so 5K parallel 100K. So let me just look into my calculator, and yeah, so this value is coming out to be 4.76 kilo ohms. So this is nothing but V test over I test, nothing but input impedance Zn, right? So we find out Zn equal to 4.76K. Now this is also known as Zn, input impedance. So we just found out that the input impedance is 4.76 kilo ohms, and this is already up to 2 decimal places. So that is all that we had to do.
So we are done with the first question. I'll reiterate that this was the problem given and we had to perform the small signal analysis. So which you can see here, that we had to perform the small signal analysis because this was given small AC signal. So we did that. We solved, if we followed a few steps, we obtained the model for this BJT small signal model. Then we removed all the independent sources like VCC over here, and then we simply put in a test source. We saw that we put in a test source and we finally solved the problem. This was, after that was nothing but KCL and KVL. That was fairly simple, but it's just that the steps are important, that the order is important, and you remove the independent sources, not the dependent sources. So we did all that and we obtained this result. So we are done with the first problem. If you have any comments, any questions, please go ahead and ask. I'll pause a bit here so that you're able to gather your thoughts. So any comments? If not, then we are completed with a discussion on BJT. Now next we'll be moving to field effect transistors. These are also, BJT is a type of transistors, bipolar junction transistor. Another type of junction transistor is field effect transistors, in particular junction field effect transistors, and in a bit we'll solve 2 or 3 of their problems. So if there are no further comments, then I'll go ahead and start solving that problem.
Statement from Gate Physics 2013 reads as follows. An N-channel junction field effect transistor has 5 milliamps source to drain current at shorted gate, also known as IDSS, and 5 volts pinch off voltage VP. Calculate the drain current in milliamps for a gate source voltage VGS of minus 2.5 volts. The answer should be up to 2 decimal places. This is a numerical answer type question, and we need to find the drain current for this problem in milliamps, and then we'll round off our answer to 2 decimal places as required and fill in the blank over here. Let's first try to understand what a junction field effect transistor is, also known in short as JFET. So on the left hand side, you can see the symbol for that is the N-type JFET. Why n-type? Because the conduction here is due to electrons. And on the right hand side you can see the p-type JFETs. So you can see that this symbol, one vertical line and these two rectangular lines, and this the symbol inside the circle is for the NJFET, and if the arrow is pointing outwards from the gate, it's known as PJFET. It's a 3-terminal device, so you have the drain, you have the gate, and you have the source. These are the 3 terminals. And why it's a transistor? Because it's the gate that is controlling how much current flows between drain and source. So that's the definition of a transistor. When the 3rd terminal gate is controlling the current flow between the drain and source. And this is a junction field effect transistor. By that we mean that there are junctions in here. So you can see for NJFET you have an n-type substrate in which there are 2 p-type regions. These are the gates. So gate is p-type while drain and source are the n-type. So effectively the current flow will happen in this vertical region, the n-type region, hence this is NJFET. Similarly for p-type you have the gate is n-type and the drain and source are p-type, and the conduction will be due to the holes for PJFET. For our discussion we'll restrict ourselves to NJFET because the discussion remains the same, just the current direction is reversed. The physics behind these devices remain the same. Right, so now you can see that so this is unbiased condition, so VGS is 0 and VDS is 0, which you can see over here. Now what we are doing here is that the gate is p-type and the drain, this is the n-type region. So naturally, even if there is no bias, there is a depletion layer which you can see in the dashed line here will form. So what happens if, let's say, we apply a slightly negative bias, reverse bias to gate source junction? So note that negative bias to gate source junction, this is p-type, gate is p-type, this means we apply some negative voltage, right? So we apply some negative voltage, so naturally we expect the depletion region to increase, because now the gate source and the gate drain also have become reverse bias. So you can see the depletion region has increased. Now what happens is that let's increase so we have applied some gate voltage, let's say some minus 0.5, minus 1 volt. So below a certain threshold, which we call pinch off. What is pinch off? If we apply such a large reverse bias to gate source, right, that these two depletion regions which you are seeing here and here, if they touch each other, which you can see happening over here, right, here the two depletion regions are touching. So here now so even if you apply, let's say hypothetically, some drain source current, no current can flow. Drain source bias, no current can flow. Hence this condition is known as the pinch off condition, and the device will not conduct. So such a voltage at which the two depletion regions merge is known as the pinch off voltage. So this is a negative voltage, because note that we are applying a negative bias. So below this the device cannot conduct. Now in order to completely understand the working, now we'll do the other case in which we'll keep VGS equal to 0, the gate source bias will remain 0, and we'll try to vary the drain source bias. So as usual, if no bias is applied, so the small depletion region will be formed here. Now let's apply some drain bias, some small drain bias. So what will happen is that, so gate drain will again become reverse bias. Note that drain is n-type and gate is p-type, and we are applying a positive voltage to drain. Gate is at 0, right? So this junction becomes reverse bias, and hence the depletion region has increased. So note that this channel has become a bit narrow, right? So electrons can still flow, but their flow will be kind of slightly restricted here, right? But so since VDS is not so high that these two depletion regions have touched, so now let's increase the depletion, and you can see some current is flowing over here, right? Because now there is a bias VDS, so electrons can flow through this channel comfortably over here, right? Right. So now let's increase the drain bias even more to this. So what will happen is that these two depletion regions will almost touch, right? And even if you increase any drain bias for now, the current cannot increase, because they're almost touching. There's a very narrow gap, so all the traffic is flowing through a very narrow gap over here, right? And so even if you increase the drain bias over a certain point, which is coincidentally the same as the pinch off voltage that we saw for the gate, the drain current will not increase. So drain current will sort of saturate, and this we can express over here, right? So you can see that after a certain VDS, which is defined here as VP, the current is constant, right? And below in the orange region, below a certain VGS, right? So this is the VGS that we are talking about over here, in this VGS, this level. Below this, there's no conduction because it has been pinched off. The channel has been pinched off and no electrons can flow. So no current is flowing over here. And this region is the ohmic region. This is the why is called ohmic, because you see the vertical axis is current and the horizontal axis is voltage, and you see a linear relation. So I directly proportional to V. That's why this region is called the ohmic region. And after a very high drain voltage, the device breaks down, because note that is the PN junction. And this is the equation that we encounter to solve for a given VGS and a given pinch of voltage. And obviously VDSS is the, when VGS is equal to 0, what is the current? So this is a good metric which is provided by the in the data sheet. So this is also in the problems you will know this. So ID is IDSS times 1 minus VGS over VP whole square. So this is the formula which we use to arrive at the current in the saturation condition. And getting back to the problem, this was the NFET NJFET that was given to us. IDSS equal to 5 milliamps and pinch of voltage is minus 5. So I've just taken it small, it's 5 volts, and VGS is minus 2.5 volts. So you can clearly see that the VGS over here, right, so it is greater than VP, because no, VGS is minus 0.5 and VP is minus 5. So this means device will conduct because it's not pinched off, right? Device will conduct. And what is the formula? So I have just denoted the currents over here. You can see IG is 0. We neglect the gate current, so we assume that no, in the depletion region, no current is flowing through the gate, and consequently ID will be equal to IS, because if like KCL over here, so there's no current is flowing in, so ID will be equal to IS. And I have denoted VD, VG and VS for just for the simplification, just so that we are able to understand where is drain and where is source. Right, and this is the formula that we'll use. We established that device will conduct. This is the formula we'll use. So we'll simply plug in the values. So IDSS is nothing but 5 milliamps times 1 minus, so minus VGS. This will be minus into minus 2.5 divided by minus of minus 5 whole square. So this will come out to be 5 milliamps times, so minus will become plus, so that will be 2.5 upon 5 whole square. So this will be 5 milliamps 1 minus half whole square. So that's 5 milliamps into 1 over 2 square. So that will be 5 milliamps over 4, which is nothing but 1.25 milliamps. So we see there is some finite current flowing over here. Note that it's not high as the IDSS, because IDSS is when VGS equal to 0, and we have still VGS as some negative voltage, right? So there will be some current flowing which is 1.25 milliamps, and so we have obtained the current here in milliamps, which was required, and up to 2 decimal places. So the answer here would be 1.25.